Ready? So I have no idea what he just said, but I'll try and talk slow so everybody understands me, I guess. So this talk is kind of about the future projects that I'm working on in cryptanalysis, and so kind of the bleeding edge of what I've been doing, and my kind of lame attempt at a keynote talk. So please bear with me here. You already got the introduction. I found out that I'm actually famous here, and people like snacks. Yeah, that's me. I'm going to cover some of the things that I've been working on. Ooh. So I started TourCon about 10 years ago. We're a hacker conference in San Diego, and that's been going for 10 years now. We also started a conference in Seattle that's been going on for 2 years now. And we're also working on having a hacker camp in the US at a Type 1 missile silo that was decommissioned about 30 years ago. And we're actually going to camp out inside the missile silo and have fun. And so it's actually going to be 4 days. It's this spring in May, and I hope you guys can make it. So one thing that we recently started was the TourCon Foundation. I know that Louise already kind of mentioned that. Basically, we earned a bunch of money at TourCon last year. We ended up using that money to buy a bunch of laptops to help a school in India that like my mom actually helps out a lot with. And basically what we're trying to do is promote young hackers to go to conferences by providing scholarships, and also maybe help fund open source projects in other countries, and try to do things like hackers on a plane to make it so people start talking to each other across borders and stuff. And so this is actually a real school. I've been there. There's a picture of me. There's my mom. There's kids working on a laptop. And before they only had one laptop, and now they have 6. And so we're kind of working on helping out these underprivileged kids. So when you see the auction later on today, that's what it's all about. I was also involved in Doc Bodum Labs in San Diego. It's a hackerspace that we started and ran for a few years. And then we also started a hackerspace in Seattle called the Public Nerd Area, or Hackerbot Labs. So I've been kind of working a lot on trying to build up hackerspaces and get people to work on cool projects together and stuff like that. And that's kind of the idea behind TourCon as well. So anyway, what I do during the day is I have a company called Pico Computing, and we make basically cool hacker gadgets that are usually too expensive for most people to buy. But basically all these cards are Express Card, Card Bus, PCMCIA, Compact Flash, and you can plug them in your laptop and accelerate breaking crypto algorithms. So we've been building supercomputing clusters and arrays using these chips. And I'll go into a little more on what FPGAs are very briefly, because I'm sure some of you already know what this is. So FPGA is a field programmable gate array, and we've put together a bunch of support for breaking algorithms using FPGAs. And for example, with WEP, with a single FPGA, we can do it about 30 times faster than a normal PC. And then WPA, file vault, and then zip, Bluetooth, and we gave a talk last year on breaking GSM 851, and we're actually selling systems for breaking GSM using rainbow tables. So there's a lot of applications on ways you can really start attacking algorithms that before were really out of reach for a lot of people to break. So I'm going to do a quick tutorial on computing, the differences between CPUs and ASICs, and GPUs, and FPGAs. So what are FPGAs good for? They're basically an ASIC that you can configure in software. And people use them for prototyping ASICs. But basically they're good at anything an ASIC is good for, but you can reprogram them over and over again. So I'll explain this a little bit more. An ASIC is basically any sort of chip that actually has logic on it. And so like the CPU in your laptop is an ASIC, the RAM, the flash, GPUs, pretty much most chips that actually do any sort of logic are considered ASICs. And how they're actually designed is you have somebody design a schematic where they put together millions and millions of gates and flip-flops and basic components, And then that actually ends up going into silicon, and you end up with tons of layers of actual transistors and stuff that end up getting actually printed or burned onto silicon wafers that go into the chips that you actually have in your laptop. And so, CPU is the obvious original thing because it's good at doing pretty much anything. In software, you can express, almost any sort of equation or thing that you want to do. And so they're very good at doing pretty much anything you want. And likewise, you can use ASICs to make things more specific, like RAM or Flash, or even like GPUs that are specifically geared towards graphics, and now are becoming a lot more mainstream. With CUDA, where you can actually do scientific applications and such with GPUs. And so the general idea here is that with an FPGA, you can design, you can configure it as RAM, as Flash. You can kind of, well, not exactly Flash, but you can design your own GPU, upload it to the chip, and then it starts functioning like that. You don't have to go through the whole process of actually making an ASIC. You can design your ASIC in software, upload it to the chip, and it functions as that ASIC. And so what we do is we design a chip that's specifically made for cracking a particular crypto algorithm, and then we upload it to the chip, and then it basically uses all its transistors towards that purpose instead of supporting the things that a normal CPU has to do, or GPUs and stuff, such like that. So it makes it a lot more efficient. You get huge speed increases, and they draw very little power because they're a very specific application. So a quick roadmap on what I'll be talking about today. I'll be talking a little bit about hidden Markov models, rainbow tables, various crypto algorithms that we've been looking at, and maybe some world domination at the end if I feel like it. So hidden Markov modeling is starting to become a little more popular with generating passwords, and so I'm going to cover what people are doing with this. Basically, if you're trying to guess, somebody's password, people have figured out that using hidden Markov models, you can basically train a model with a bunch of passwords and use it similar to speech recognition, handwriting recognition, bioinformatics, and other sorts of ways that people use hidden Markov models for basically modeling data sets. And so essentially how it works is that if you have a simple password like A, B, C, you just model the state transitions from A to B and B to C. And so you can see that you have your start point, and then that always goes to A, and then A goes to B, and B always goes to C. And then same, a simple example here, A goes to B, and then B goes back to itself. So when you start looking at longer passwords or more passwords, you can start feeding it into the model, and then if you actually combine both of these together, you end up with A going to B, and then it has a 50% chance of going to B again, or a 50% chance of going to C. And so that's an easy way of expressing these words using hidden Markov models. And it becomes a lot more complex when you're actually using real passwords, but that's the general idea. For example, you end up with slightly more complex structures when you add other things, and then typically your model will have A through Z, 0 through 9, and then special characters and stuff like that. So it can become a lot more complicated than just this. And then there's other ways of putting together your models so they become more specific. For example, what I showed you before was a zero order model where it only looks at the character, the current state that you're on. And so once you're at the A state, all you know is to go to B. And once you're over here, then all you know is to go to these two. Whereas in a first order, you actually look at the previous state that you had. And so once you're at A, if your previous state was S, then you always go here. If the previous state was B, then you jump there. So basically the general idea is that there's lots of ways to structure your hidden Markov model to be better at generating passwords. And so there's lots of different ways of configuring it. And one thing that's interesting about this is that people have actually been using this for a while to generate passwords that people remember. And one of the arguments is that in your brain you kind of use something similar to a Markov model to actually remember words or identify words that you see. Just like if you see a random word without any vowels in it, it doesn't look like a word. But if there's vowels, after certain letters, then it looks more like a normal word. And that varies between languages as well. But the cool thing about this is that you can train it, for a certain language, and then it'll just start generating passwords that fit that language. So people have actually been using this for a while for generating passwords. And so the obvious black hat approach is to use the same thing to crack people's passwords. So one thing that's kind of cool about this is that with using FPGAs, we can basically put a model on the chip and then have it start generating passwords instead of actually having to upload a huge word list onto the chip. And so it makes it a lot more efficient. And the cool side effect is that it'll generate lots of extra passwords. And so if you have a word list of only a million passwords, you train it, you can start generating billions of passwords that fit the model. And so it'll start finding the passwords that are part of your list, as well as making its own sort of interpretations. And so it definitely helps out quite a bit. So one example, I just did a simple implementation using like a very basic markup model. You end up with words that look fairly like pronounceable, and just using rand, they don't really look as much like words as just normal H1. And so with this, you can also make it a lot more specific and make it closer to the actual passwords. But the cool thing is you can actually tune it quite a bit. So the general idea here is that usually when you're cracking a password, you have kind of the option of either brute forcing the entire key space, or just looking at words in a word list, or like modifying the word list using permutations and such to make a bigger word list and trying an actual word list on it. The cool thing about Hulton Markov models is that you can kind of tune how far you want to go in between the entire key space and the word list. So, for example, like you can say I just want to target a smaller subset in between, or you can say I want to target more passwords. So I'm going to talk about rainbow tables and FPGAs. So I'm sure a lot of you are already familiar with rainbow tables, but it's basically a way of doing a lookup table where you don't have to actually store the entire lookup table. And so it's a time memory trade-off where you can say I only want to store this amount and I don't mind computing the rest of it in real time. So one example is if you're breaking a landman password, there's roughly 69 to the 7 possible passwords, give or take. And if you actually generate that many hashes, if you take all the possible passwords, generate all the possible hashes, and store it trivially on a disk, you'll end up with taking up around 120 terabytes of storage. And so that's not very practical. So rainbow tables basically let you say, okay, well, I don't mind storing 4.2 gigabytes, so I'm going to store that amount. And then I don't mind computing 2 to the 15 whenever I want to crack a hash. And so technically it takes you 32,000 times longer to break your hash when you actually want to break it. But because you're doing these operations, thousands of times per second, it's actually fairly quick. And so you can really scale it based on that. One thing that's cool about this is that with FPGAs, if you can accelerate, this time thing here, then you can start actually attacking key spaces larger than 2 to the 43. For example, with our GSM table, we're attacking basically 2 to the 58 and doing it in close to real time. So there's lots of ways that you can start attacking even larger key spaces, such as like for DES or algorithms with larger key spaces. So what we found is that oftentimes you can start attacking things 12 bits larger than what other traditional rainbow tables can attack. So one thing that was interesting is that a couple years ago, this paper came out that not very many people realized, where it actually takes rainbow tables and combines it with hidden Markov models to create more efficient rainbow tables. And so out of the 69 to the 7 possible passwords for landman, there's actually a very small subset of that people would actually use as real passwords. People aren't going to use, like just random special characters as their password, unless, it's people like you here. But the really cool thing about this is that you can start specifically gearing your rainbow table towards more probable passwords based on, a training model. And so the side effect is that you can start attacking larger key spaces with actual less space, and really how it works is with a rainbow table you end up with this reduction function that transforms your hash into an actual password. And normally they just do mapping of that directly to a password. But what you can do is use a hidden Markov model as your reduction function instead. And so instead of mapping to an arbitrary area in the entire key space, it actually can start assigning that in a more probabilistic fashion. So traditionally, rainbow tables don't work on key spaces that are too large because it'll take too long to actually compute the rainbow table, and they don't work on salted algorithms. So with this, suddenly you can start attacking larger key spaces. For example, with NTLM, if you're trying to attack a password that's 16 characters long, you can start saying, okay, I'm pretty sure the guy's using a 16-character password, but only attack the most probable passwords out of that, the most probable 16-character passwords. And so you can start, gearing your rainbow table towards that sort of, statistical model. And also with salt, traditionally with rainbow tables you can't attack them too slow. And so the reason for this is that once you have the salt in there, you actually have to create a rainbow table for every possible salt. And most of the new schemes use salt, so I'm going to cover this a little bit as well. If you look up salt on Wikipedia, they actually have a nice description of it. The benefit provided by using a salted password is that a simple dictionary attack against encrypted values becomes impractical if the salt is large enough. And just stopping there, the salt has to be large enough. And so it turns out that actually the old standard Unix DesCrypt only uses a 12-bit salt. So one thing that's interesting about this is that if you use hidden Markov tables, you can actually start attacking these sorts of passwords because you only have to create 4,000 rainbow tables, which is actually fairly easy. And especially with FPGAs, I did some quick calculations, and it's very rough. But if I happen to use like 120 FPGAs laying around in the office, and they run them for about a month, I can basically create rainbow tables for all the possible salts, and each one will have about 1/64 of the entire key space. But it's actually not that bad if you end up cracking at least 60 or 70% of all the possible passwords that people actually use. And so that's one thing that you can start using with this combination of attacks. So the lesson here is obviously use a larger salt value. 12 bits isn't enough. Newer algorithms start using like the newer version of Unix uses 24 bits. Not many people actually use that. A lot of other algorithms use 32-bit salts, and that's very good. And so you think to yourself, okay, well, obviously everybody else must use salt these days, right? Surprise. I decided to deem these MSG-grade crypto because they don't use salt. And so Landman, we already know that that's broken. There's no salt with Landman. NTLM, no salt. Many DES implementations don't use the salt. MySQL, Apache, Office 97, PDF 1.3. There's lots of stuff out there that actually still doesn't use any sort of salt, and a lot of stuff that has low enough strength crypto that you can actually create rainbow tables for it. So just looking at Landman here. Another interesting side effect is that, I don't know if anybody here are familiar with the challenge response for Landman and NTLM. Aside from the many other vulnerabilities, they actually use DES for their challenge response. And And obviously, they just use straight DES, and it actually has a fixed key and all sorts of stuff. So you can actually start attacking challenge response and sniffing landmine hashes and stuff like that. I mean, just using a DES rainbow table. So DES rainbow tables are easy to put together these days, but they have to be geared specifically for an application, and that's the only thing. So if you guys know of any other applications that use DES that you think we could build a rainbow table for, please let me know later. And so yeah, basically something like this is perfect for a rainbow table. And actually building a DES rainbow table, if we actually use 120 FPGAs, we get about 50% collisions. It will only take us about 13 days to build the rainbow table, and then we can do real-time decryption with these FPGAs and with about 8 terabytes of storage, which isn't too bad. Or about 2 minutes if you only have one FPGA. And so we could start distributing this for a couple $1,000. People could start actually breaking DES in a matter of a couple minutes. So looking at Office 97, there's already 40-bit rainbow tables provided by the same people that do off-rack. And I'm still looking into how they actually do the password hashing, but it's possible that you can start using data Markov models and FPGAs to attack the 128-bit version. Also PDF, I've also verified that you can actually start using HMMs and FPGAs to start attacking 128-bit. And there's already 40-bit rainbow tables provided by Elcom Soft, I believe. So now we can start attacking an even stronger PDF encryption. So now I'm getting on to the world domination part. Where's security going? And what are you actually going to learn from this presentation? I know it's a bunch of crypto stuff, but how can this apply to other sorts of things? So obviously, if you're finding new classes of attacks, you end up with some code that you audit, and then you attack it, and then somebody fixes the code, and then you audit and attack it, and so on. And so there's this whole cycle where as new code comes out, obviously there's going to be new attacks, because if they fix the old ones, then you have to find the new ones and stuff. So I think that we're always going to be finding newer classes of attacks that will be more complicated, but they'll always be there. And another thing is that using just existing classes of attacks, there's already tons of vulnerabilities out there. There's still buffer overflows that existed decades ago. So, I just picked this because people are even buffer overflowing, Dilbert now, so. And another thing is that there's a lot of attacks out there nowadays that just using one class of attack isn't enough. Actually combining multiple attacks together starts attacking new things. And so one example, the cold boot attack that Bruno will be talking about later. It gives you access to all the PC's memory, but it's only really useful if you have some secondary sort of vulnerability, like people not zeroing out keys in memory, algorithms for actually finding keys in memory, and specific uses for this attack. Same with like the Dan Kaminsky DNS attack. Opens up a lot of new vulnerabilities, but you still have to start implementing vulnerabilities to actually use it. Putting together a phishing site, attacking auto update. There's lots of combinations where initially auto update vulnerabilities were only really useful on the local LAN when you're randomly milling somebody, but now that you can start doing a DNS cache injection, then you can start attacking stuff over the internet. So I think that it's important to also look at how things combine together, the real scope of all of your attacks, and how they affect each other like this. And I still think that there's a lot of interesting research to be done in lots of areas like this. So just going back to earlier, these are all the algorithms that we support or we're going to support in the future for breaking. And I've kind of classified them into ones that are less than 50-bit, in that it's possible to do a PC rainbow table attack on them. Ones that are less than 64-bit, that are where it's possible to do an FPGA attack. password-based ones, where we can start using the hidden markup models to attack. And then some of them don't use any salt. Some of them use a little bit, like descrypt, and some of them use salt. So I'm just going to eliminate all of the salted ones because we can't really do rainbow tables for those. So just off the bat, obviously with PCs, you can do LAN, you can do 40-bit Office, you can do 40-bit PDF. And right after the hidden markup model paper came out, suddenly, people should realize that all these sorts of things are vulnerable as well. And now you had FPGAs, and now you can start attacking, the 64-bit sort of algorithms. And so really, all of these are technically vulnerable, and they've been vulnerable for a while. But people just need to, realize these sorts of things. And currently, pretty much all of these are brute forceable. If you have a really complicated password, there's no way that we're ever going to find it for certain algorithms like WinZip or FileVault or more complicated algorithms. But they're all, pretty much attackable for simple passwords. So another interesting thing to look at when you're looking at vulnerabilities is how will this, how will this be in another couple years? And so one easy way with crypto is people look at Moore's law. Basically, Moore originally said that transistors double every 2 years for the amount of surface area. So you can see over here, we originally started out with like 4,000 transistors on a processor. Now we're up to like 100 million transistors. And pretty much all of these occupy the same amount of space. And so because inherently when you end up with smaller transistors, the switch time is a lot faster. You can have faster speed of a processor. People say that Moore's law is performance doubles every 18 months. And so if you really think about it, computation performance goes up 10x every 5 years, 100x every 10 years, 10,000x every 20 years. And so if we start graphing this out, just looking at algorithms that are out there, this is the PC down here, which is, currently we're at the possibility of doing maybe about 40 to 50 bits. With FPGAs, we're easily in the 60-bit range. And ASICs, if you actually have millions of dollars to spend to create your own chips, like if you're an intelligence agency or such, you can start breaking stuff that's even higher. And really all this depends on your budget. But I guess the main thing is that a lot of these things are easily attackable. Even just looking at SHA-1 collisions, it's only rated at 80 bits, and so in the next 20 years or something, it'll be easy for anybody to do it. And it's already getting fairly possible for people to do it in like for a particular hash and such. And there's some algorithms where if they actually are rated at 128 bits, it's going to be a long time before we get there. And there's arguments that there's more protons on Earth than or less protons on Earth than 2 to the 128 and such. So it'll be interesting to see how Moore's law progresses and if these things will actually be able to be attacked practically in the future. So I guess that the whole point of this talk is that security is an iterative process. It really takes an understanding of the whole system, how everything fits together, understanding different attacks and how they affect each other. And you can't always use just a point-and-click solution to fix a lot of your problems or to find lots of new vulnerabilities. And just because something's secure today doesn't mean it'll be secure tomorrow or 10 years from now or 20 years from now. A lot of these systems that people designed, like Landman back in the late 80s, they're going to be around forever. And I mean, they're starting to get rid of them, but it's already been 20 years, and so there's a lot of things where initially you think that you'll just be using it for a little while. You can always patch it later, but a lot of these things end up dragging on for longer than you really expect. So I'm almost done with this presentation. I guess one of the main messages is that there's a lot left to be done. There's a lot of areas of research that are left to be explored, and I think all that we know right now is just the tip of the iceberg. So definitely have fun, go out, find new vulnerabilities, and beware of those hackers. I don't know where they are. I think there's some of them in Brazil, but beware. So if you have any questions, feel free to buy me a drink, at the risk of me maybe dressing up like Michael Jackson accidentally. And here's some URLs you can check out to work on. Hope you come to the camp. For now, are there any questions? Or?
Uma pergunta, alguém? Não? Vai para aqui, paga uma cerveja para ele. Vai. You're gonna buy a beer.
Oh, okay, all right. Okay, thank you very much.